Hello, everyone, and it's time to start one of my favorite lectures on experimental design on the issue of confounders. But before we do that, I just want to make sure that everybody knows what the due dates are here, and the chapters 1 and 2 pre-lectures. It looks like they're due on Friday, but read carefully, they're actually due on Sunday. So I moved those up to allow for people who are registering late. And the bonus is always going to be due on Sunday. I've just moved that up to allow for these R assignments that we haven't talked much about to be due on Friday. Because when I was thinking about it, if I have R assignments due on Sunday, you're going to run into problems over the weekend and you won't get any help. So I want you to be able to get a lot of help because computer glitches can always happen and it's so frustrating. So we have office hours 2 to 5 p.m. every day on the second floor. I'll show you where just to make sure you know. So the office hours are every single afternoon, 2 to 5, in 703 South Wright Street, okay? On the second floor, but they don't start until next week, which is fine, because if we look back at the calendar here, this R assignment, which you're going to probably need the office hours more for the R assignments, just because, you know, for a lot of you, you haven't ever done any programming at all, and lots of times there's computer glitches. But I hope you come to for help with the homework and the pre-lectures and all of it, or any questions that you have. I welcome you to come. There's always going to be an instructor there, either me or one of the other section instructors, plus student educators. So just stop by. It would be a good place to do your homework. And any questions at all? So one question I've got is, go ahead, there's a question.
What if we can't make those office hours? I actually have work basically 2 to 5 every day.
Good question. What if you can't make those office hours? People work, especially online people, in class people. So if you can't make those 2 to 5 office hours, we can just email me or your instructor, if you're in a section, and we'll set up other times. We want to accommodate everybody. And we can do a lot of help. Just all of your homework and all of your R assignments are going to be done on Lon Kappa. And Lon Kappa has great discussion boards underneath, especially great from my point of view, because if you ask a question on Lon Kappa, I can just, first of all, it's right under the problem you're having. So it's right there. I know which question you're having difficulty with, and then I can click on your response. You can post anonymously, but I can still click on it. No one else can see you, but I'll know who you are. And I can click on it, and I can see exactly the homework problem you got, because everybody gets a different one. They're randomized, different numbers. So I can see exactly what you got and your previous wrong answers and can tell what the trouble is pretty easily. So I can answer it. And often I really welcome, lots of times you ask a question that a lot of other students have had the same difficulty, and they know how to answer it faster than I do, probably, in many cases. So always post on those discussion boards as your first step. They're amazingly good. People don't use them enough. And it's a great place for you guys to help each other. And it's really hard to give away the answer because so many of the questions are randomized. So you really have to explain the method. This is what you need to do. You can't just say, hey, the answer is such and such, because it won't be for most people. Except for, some of the beginning assignments where they're multiple choice, or like the ones on experimental design are not randomized so much. So there you have to be careful to not give away the answer. So, yes, another question, yes?
Are the R assignments due at 11:59 on Fridays or before class?
Good question. He asked, are the R assignments due at 11:59 on Friday? Yes, every single thing that you submit, whether it's online Kappa, which is all your submissions, is always due at 11:59 p.m. Okay? Of the day that it's due. Yep. So, any other questions before we begin? All right, so then let's just go over to the document camera here and get started. All right, so we are on page 5 in our notebooks today, and we're going to be talking about observational studies. Remember, last time we talked about experiments. And in an experiment, the researcher chooses who's in the treatment group and who's in the comparison group. And we saw that the ideal way to design an experiment is to use something called a randomized controlled double-blind experiment. And the goal being that we want the treatment, just to refresh your memory, we wanted the treatment and the control group to start off as balanced as possible at the start of the experiment before we give a treatment. So we have a treatment and a comparison group, and we want them to be as alike as possible. And we saw that randomization, blocking first and then randomizing at the final assignment, is the best way to make sure that the treatment and the control groups are alike on all characteristics, not just the ones you think are important. We can block on the ones we think are important, but then the final step is randomize, and then we know that that even on hidden characteristics that we might not know about, they'll be balanced. There'll be accidental differences with small samples, accidental differences, but with large samples, accidental differences average out. Random differences average out in the long run because they're going in both directions. You know, sometimes you'll get too high, sometimes you'll get too low, so they average out in the long run. But systematic differences, bias, doesn't average out because it's always going in the same direction. So it doesn't matter if you have a bigger sample, it doesn't average out. So that's the idea. Now we said, here we are, now we're talking about observational studies, and we said that why don't you always do experiments? Because lots of times we can't, like right now. The experiment you guys, the study that you guys are involved in, comparing online education to in-person, online classes to in-person, is, as much as I'd like it to be randomized, at this point, I don't have buy-in from the registration, I don't have enough buy-in from students, because people don't want to be randomly assigned to one section or the other. They want to choose at this point. Maybe after this class, when you see how important it is to do randomized studies, you'll have a different feeling about that. We'll see. But, so what's the problem? There's differences when people choose, or the researcher chooses, or even fate chooses. There's systematic differences between the treatment and the control group. They start off, they're unbalanced to begin with. So any responses you see at the end are confused with the differences that were there with the start. It's very confusing. And so what do you do? So that's the main problem with observational data, is that it has what's called confusers or confounders, differences between the treatment and the control group that make it hard to tell when you're looking at the response, if you see an improvement, was it due to the treatment or was it due to the differences at the start of the study? So that's the problem, okay? So observational, you can see two things associated with each other, but how do you know whether it was the treatment that caused the response, caused that, or whether it was some other difference between the groups? So it's a very that's what we're going to be exploring now, how we can get at causation even in observational studies, and how we're doing it right now in the study you're involved in, okay? So the question always is, did the treatment cause the response? You know, you see two things associated. Like right now, let's just look at what we've been looking at in Stat 100 data, that we see that the online students had better scores at the end, better results. So was it the online education, the treatment group, you can think online versus the traditional in class. Was it the online delivery system that actually caused the better scores? And if so, how? If so, how? This is like what we would be very interested in that. How does it do it? So this would be like the causation pathway that in this example, like if we were saying, does the online, we see online associated with better scores at the end. Higher scores. Now, is it a causal relation or is there a confounder? We don't know. There's probably some confounders. We found some already. So online, because it's an ops and better scores. All right, so the causal link is if the online's really, the delivery system is really somehow causing this slight, it's not that big, improvement in exam scores, then how is it doing it? We want to know how. So this causal link is, think of it as a causation pathway. I mean, what about the online class? Is it because students can watch the lectures at their own pace, or they actually can watch them multiple times? What about it is doing this? And this explains how the treatment is causing the response. That's the causal link. Now, or it might be this, or because it's an observational study, there's bound to be some confounders. So what's a confounder? What is that? A confounder would be a third variable. The simplest case of a confounder would be a third factor that's causing both the treatment and the response, making it look like there's a causal relation between the treatment and the response when there's not. So it's a confuser. So for example, one confounder we have identified that made a big difference in a few classes is that the people who are choosing the online, the students who are choosing the online, had higher math ACT scores. So we could say better math skills. And maybe they just felt more confident and they chose the online. Might have been true in the beginning. It might not be true now. We haven't analyzed recent data. So better math skills were causing them to choose the online. And then, of course, because they had better math skills, they were getting better scores. So once we removed that effect of that confounder, we found no difference between the online and the in-person groups. So it's not in this case, had nothing to do with the online education. If these students had been chosen the in-person, they would have done better too. It's just that, do you understand, it's a third factor affecting both. And that's a confounder. And why is it important? Because it's mysterious. When we first saw this, we didn't think about this. When we first thought, we said, oh, we're in this situation. But then once you realize it might have nothing to do with the online. This might happen anyway. So we can come to erroneous causal conclusions if we don't carefully eliminate confounders. So a confounder, think of it as a confuser. It wouldn't happen in randomized experiments because there's no systematic differences. If you were randomly assigned, to treatment and control. Would we see that? Would you see one group having systematically higher ACT scores? No. Just accidentally, you'd see little differences, but not systematic differences. So it's a difference. It doesn't happen in randomized studies. It's a difference between the treatment and the control group that confuses our results. Making it look like the treatment is causing the response when it's not. The treatment is causing the response when it's not. Okay, so this example I talked about right here, just so if you want to look back at it, this example is on page 9. So that was the example we just looked at. I'll show you what it. On page 9, I said in online Stat 100 in higher exam scores, we found that Stat 100 online students taking the same exact course as Stat 100 in-person students did significantly better on the same exams. Does that mean that watching the lectures causes Stat 100 students to score higher? Maybe, but we have to first eliminate the confounders. Okay? Maybe it does, maybe we don't know. That's why we have to think about it. Think about these two scenarios here. Okay, so I should tell, I said that randomized experiments don't have confounders, so let's write that down. That's one huge advantage of being able to randomly assign people to the treatment and the control group. And that's the best way to find out if a treatment really works or doesn't. They can have accidental differences. They can have accidental differences, but with a big, large enough study, or if you block first, then you can get rid of a lot of that. Because treatment and control start off balanced. Then you introduce the treatment, and then any differences you see at the end have to be due to the treatment because everything else was the same. So now, our goal is to make the treatment and control groups as alike as possible. And how are we going to get there with observational studies that start off so unbalanced? What we do is we stratify. That means we break the subjects into subgroups that are more like each other, and compare the responses within those subgroups. So stratification plays a similar role in observational studies as blocking does to randomized experiments, but it's much more important because it's the only way we have. Remember, if the randomized experiment is large enough, we're not going to really have systematic differences. There's not much need to even block. But with stratification, with observational studies, no matter how big the study is, we are going to have big differences between the treatment and the control group. So we want to compare apples to apples, so we have to break them into subgroups along what we think that confounding factor is that's creating the difference, like better math skills, different ACT scores, whatever it is. And we would want to ideally take this, if you have a big enough group, take everybody who scored a 30 on the ACT and in the online and compare them to everybody who scored a 30 in the in-person group, and then see if the differences disappear or not. They might even go in the other direction. It might be that the online is worse. You know, it's very interesting. It's a mystery. Think of yourselves as statistical sleuths or detectives. If you're analyzing your own data, which you can be in this class, you are the best detectives for all of this, because you understand what factors go into people choosing one class over another, what factors go into that might escape other people. So I've had students do very extraordinary data analysis, very creative and original, that I wouldn't have even thought of when it comes to this, because you know what goes into what ingredients go into it, and you can be better detectives than somebody that's more divorced from student life. So I think it's exciting, it's fun. So let's just say, so the difference, don't get blocking and stratification too confused. They're similar, but remember what? The blocking happens at the start of a randomized experiment, okay? And stratification happens at the end of an observational study. Blocking, is done at the start of a randomized experiment. Okay, don't want to hit anything there. And stratification, you can't do anything at the start of an observational study, really. Well, I guess I could, because I can't make it, not in terms of who's assigned to treatment and control, and this, I can't, really. It just, you do that, and then you just analyze the results afterwards. So stratification is done at the end of an observational study. And that's, it's just detective work. And like detective work, it's almost as much of an art as a science. It really is. So for those of you who like to combine those two things, it's very exciting. Okay, now, so how would it work? How does stratification work, and how does it compare to blocking? So why don't we just take that same example that we had before where we blocked. The example was if we were doing a study to see if some drug, it was an imaginary study, hypothetical, to see if some drug helped students learn stats, right? That was the idea, and we did that blocking example. Right here. And we said, okay, we blocked because we wanted to get, even though we're randomly dividing in both cases, we wanted to avoid, in a small study particularly, these big accidental differences. So there's still random division. Okay, but the difference is, if we blocked first and then randomly assigned it, everyone still has the same equal chance of being in treatment and control. We've just reduced accidental random variation, which is what you want to do. The idea is everybody has the same chance of being, it's a planned introduction of chance. It doesn't affect bias at all. Okay, so that's blocking. Now we're going to look at the same exact data, pretend there was a class where instead of being randomly assigned to the treatment, remember what it was? It was a drug, was the treatment, and the placebo was the control. Now, if students are choosing, should we have a placebo? Does it even make sense? They're choosing not to take the drug. So you can't give them a placebo. It would make no sense, right? So so now we're going to have no drug here. All right. So suppose these 36 students were allowed to choose themselves. All right? And let's say, we're going to get uneven groups. Let's say they chose that same division. So there's going to be unevenness, and let's say this is the way they chose it. The same thing we got before. Now, the students chose, there's no random. So we're ending up with these completely lopsided groups. So if the treatment works, if these students in this group end up with higher scores, they do better, there's no way we can tell whether it was due to the drug or to this imbalance. They were better students to begin with. So how can we separate those two things out? We stratify. This is like a layer. We stratify. So we compare A's to A's and B's to B's, likes to likes. Okay? You stratify to eliminate the confounding effect of, these are A's before, what do I mean A's and B's? These were in prior math classes because, we're doing this, they did this at the start of the study. They haven't gotten their grades in this class, in this stats class, but in prior math classes. This is 13 people had an A average and 5 people had a B average, let's say. Okay, so now we compare, well, the A's to A's, well, that's good, but is this a problem? We have many more people here than here. So we're going to compare their overall, it's not a problem because we are going to compare the average grade of the 13 people compared to the average grade of the 5 people. So when you compare averages, that takes into account that we have more people here than we do here. Do you understand that? Just because you have more people, that doesn't mean you're going to have a higher average. So we're going to compare the averages, so that doesn't matter. The number difference doesn't matter. And same here. So, look how small our sample is. That's a problem, all right? We really made our sample size pretty small here. So what if we stratify our comparison groups? They get smaller. And remember, when you get smaller, even if we're comparing likes, there's more room for chance error, right? So, and also, there's not usually just one confounder, right? There's multiple confounders. What if we also thought income was a confounder, that had something to do with why people were choosing one group over another? That means that we're going to have to stratify again. So we'd have to break the 2 subgroups into 2 more subgroups by income. And let's see what would happen if we did that. If we did that, we have so for the drug group, what we'd have to do is take those 13 A's here and divide them into 3 more groups and the 5 B's. So we have the 13 A's and we have the 5 B's. And if we divide them into 3 more groups, 1, 2, 3, let's say high, middle, and low, if we wanted to divide them into 3 groups by income, you could have more, but we don't have enough people to have more. High, middle, and low. Look, already with 5 people, you're only going to get 1 person in one of the groups. You might get nobody. So that is and then you do the same thing with the no drug group, the treatment and the control group. And you divide them into 3 groups, high, middle, and low. And oops, I should do it the other way. You have the 5 A's here, right? You don't have 13 A's. Otherwise, we wouldn't. You have 5 A's. And you have 13 B's. High, middle, and low. And then what happens? We really don't have enough data to do this. We really don't. We're going to have no people probably in one of these groups, or just 1. So we don't even have enough data to do that. Well, if we had 3 groups, we certainly wouldn't have enough data. Let's say we had, if we had another confounder, but some of the groups would be empty or have just one person. So one way to deal with this instead of stratification, and what you'll see a lot, is modeling. Basically, including another way to stratify would be to include the confounder as what's called a covariate or a predictor variable in a regression model. So that would be, that's what we're doing with our data, and that's a nice way to do it. So we're going to explore modeling in chapter 28. And we'll spend a lot of time comparing that to stratification. I mean, stratification is great. That's what you want to get at with modeling. It gives you all the information, but you need a huge sample size, and it gets confusing. So people like a simpler model. So this is important. With the observational data, you need a much bigger sample size than you do with experimental data, because each time you stratify, the comparison groups get smaller and smaller. So one way to deal with this is modeling. That's going to be a big part of our course. Linear models is really what the course is about, but it's going to take us a while to get there because we're starting at square one. Okay, now, so this, as I said it and in my intro, that I learn best through examples, and I think many students do as well. If you pick the right example, it sticks in your mind. So here's an iconic example that I think is very helpful to think about when you think about confounding. All right? So we're going to start with this extreme example that will help you remember what a confounder is. Lighters and lung cancer. Now, stay with me because you're going to think that's ludicrous. Lighters don't cause lung cancer, but the logic is the same. There is an association between people who carry lighters and people who get cancer, right? There's a correlation there. And it's an observational study, in observational studies. So we're really in the situation where we don't know whether lighters cause cancer, they might, right? Or whether lighters don't cause cancer. So we're in one of these two situations. So I want you to think about it. Do lighters, if lighters cause cancer, lighters cause cancer. And that's why we're seeing this association. We're seeing this association because the arrows might go this way. That the lighters, there's some causal pathway. How do they do it? That's what fits in here. How? Or we're seeing this association because of a third, sometimes called lurking variables, a confounder that's really causing both the lung cancer and causing people to carry lighters. So lighters don't cause cancer. It just looks that way because of a confounding variable. So you have to think lighters don't cause cancer, right? We know they don't, but it's a good example because you already know it, you know? It's ludicrous. Maybe they do, though. Lighters don't cause cancer, but you have to answer this question. If they don't cause cancer, this is the question you want to know. So why? Why are these two associated? Why are they correlated if it doesn't? That's what we're trying to get at. So why are they correlated? Associated. All right. So this is very similar to your homework, and this is an example that you could hold in your mind when you do much more complicated examples that aren't obvious. So below are either possible confounders that would fit into this mystery box. mixing up the results, making it look like lighters cause cancer when they don't. All right? Or below, there might be these causal links that would fit inside this box explaining how lighters may cause cancer. How? There might be some causal pathway. How? So it's a possible causal link here. Or neither. And this happens all the time. People think confounders are just another cause of the response. But so they get all, it's very mixed up. Yeah, there's going to be lots of, but we're interested in this particular connection. So other causes have nothing to do with it. Cancer can be caused by lots of different things. Don't think those are confounders. They have nothing to do with this association. So a confounder has to be connected to both of them, and not just neither. Those are causes of cancers, but ones that don't explain why people with lighters are getting more cancer. They're not on the cause. They have nothing to do with the lighters, and so they're not helpful. They're just extra. We might be interested in them for another reason, for sure, but not when we're trying to understand whether this treatment causes this response. Okay, so let's just do the first one together and see. And I want you, this is important. I know you have a lot of outside information that you want to bring in, but for the purposes of this, we're just looking at the logic here. And so just use the information that's given for these examples. Okay, we're just testing the logic of it. So don't bring in any other outside information, just what's given here. So genetics. So assume what I'm saying. Some people are more genetically prone to lung cancer than others. So where does that fit in? So does it fit in here? Genetics. Genes cause lung cancer, so that's what's saying, okay. But do lighters cause the genes? No. So that one is eliminated. How about here? Some people the genetics causes lung cancer, yes, one of the causes. But does it also cause lighters? No. So we know it's not there. So the way you should think about it is to write, okay, we have this treatment, lighters, and we have this response, cancer. And we want to know how these arrows go. And so we put genetics in here, or genes, and it says, so this is telling you, this explanation, that genes have some influence here. But there's no information, nothing about this connection, right? And even it would be kind of hard to think of one. So there's nothing about this connection. So there's no link with lighters, so it's neither. Okay? There's no link with lighters. There's no mention of lighters, nothing. I'm going to put a question mark. That's what that is, because there's nothing there. There's no arrow. Okay? How about you just do the rest, and I'll give you a few moments, and then we'll look at them. So you can discuss it or just circle your answers, what you think the rest of them are. Look up when you're done so I can get a feel for when you're finished. And feel free to talk to each other. These desks are great in here because they move around. So you can just scoot over and, ask anybody you want a question. I like the setup in this room. It's great for group work. Hey, and you guys at home, this is the best use of this model is that you can stop the video, not just when I pause it here. Now you could speed it up if you're done, but you could stop it if you ever think that you already know how to do the examples. Just go ahead and do them, and then you can see if you got the right answer. I know the people who really do, who've been most successful in the online course have done that. So that's my advice, to use it more interactively, control it. All right, so now back. Let's see, what, anybody want to say which one is a causal link and why? Yes, over there? Okay, lighter fluid is a causal link. Let's try it. How many other people thought that? Okay, so lighter fluid. What does it say? Perhaps inhaling the fumes from lighter can cause cancer via lung damage. So it's pretty much giving you that causal pathway here. Lighters have fumes that lead to lung damage. Fumes lead to lung damage that cause the lung. Oh, so sorry. Lighters have fumes. It fits in that box. Everybody see that? Okay, so that's good. And it might be true, but it's probably not a big effect if it was. Okay, now how about a confounder? Which one was that? Was there any confounders here? Go ahead. Smoking cigarettes, huge confounder. So smoking. Let's see how it was explained. People who smoke have a higher rate of lung cancer and are also more likely to carry lighters. So it's connected to both of them. Smoking causes lung cancer, and smokers are smokers are more likely to carry lighters. Smoking causes them to carry lighters. Not all of them, but some of them. All right, so that's a confounder. That's really good. Let's look at these. These ones might be harder. Age. So you think age. Lung cancer rates rise with age. Okay, so age, you're more likely to get cancer. But again, there's nothing to do with lighters here. There's nothing mentioned, and I don't, if it said older people are more likely to carry lighters, but no. So that is neither. And radon. So radon exposure it is a big risk for lung cancer. Radon causes lung cancer. But again, that doesn't explain what we're interested in. We're interested in whether lighters cause lung cancer. Radon does, but what does that have to do with lighters? Nothing that's mentioned, at least. So that's neither. All right? In all of these, we want to find out whether people should stop carrying lighters or not. And these ones that have another cause don't help us with that. Okay, so now that we think that smoking's the confounder, how would we stratify and what would it tell us? So here we are on the next page here, page 8. How would we stratify? What does it mean? So let's just look at our picture here. We have this observational study, right? The treatment here is lighters. The control is no lighters. And then we have this response here. That's lung cancer. Okay. So we're in this situation because it's an observational study. This is where we are in this situation. So the problem is, what? Is it the lighters that's causing the higher lung cancer rate, or the unbalanced groups, because there's more smokers here in the lighter group, and here there's less smokers. So our problem is, when we see this high cancer rate, we can't tell whether it's this confounding variable, smokers, is it the smoke, or the lighters, because they're mixed up. So what we want to do is stratify, eliminate the effect of this confounder by breaking into subgroups. where that confounder is the same. So we want to get rid of it. Let the first thing, no smokers. Compare, let's break it. Here's the stratification. Let's compare the lung cancer rates of those treatment to control when nobody smokes. So we've eliminated that, right? Now, we could make as many groups as you want. Ideally, if you had a huge study, you could do, 10 cigarettes a day or a pack a day, etc. But let's just do 3 groups here. Moderate smokers. Everybody smokes at about the same level. But what we're interested in is the cancer rate of those who carry lighters greater than the ones who don't. And same with the heavy smokers. So here is the visual. We break it up into the 3 groups. So these are the non-smokers. We still have the treatment and the control groups. And just to remind you, these are the lighters. And these are the no lighters. And here's what happens in this example. When we do this, that this cancer rate, this is our cancer rate, the lung cancer rate, is very low for everybody here. Very low. And there's no difference at all between lighters and non-lighters. Now we can look at the next group, because it doesn't always have to be the same. It can affect one group and not another. So we can look at the next one. Now you might say, well, how are there no lighter people who don't smoke? I mean, how are there lighter people who smoke? There's most people who don't smoke aren't going to be carrying lighters, but people could be carrying lighters because they like to light candles, in their home or whatever. They could be carrying lighters for other reasons. And it doesn't matter if there's more of one rather than the other, because we are comparing rate and average of the people, the average rate in each group. So it doesn't matter, there's going to be a lot more of these people in this group. Okay, so now the next one would be the moderate smokers. And then this would be heavy smokers. And within each one, we're comparing lighters to no lighters, lighters to no lighters. And look, this confounding variable is gone, so there's no mix-up here. That's gone. Everybody in this group. And then if we see that the rates are the same, look how I drew it this way, because everybody in this group, they're heavy smokers. This tells you that smoking is causing cancer. They are getting cancer more than the moderate, more than the non-smokers. So it's a dose dependence curve line here. And so that shows you smoking is doing it, is a cause. And it also shows you that the lighters don't do anything. There's no difference. So that's the idea, and I should just write that down here. Since the treatment and control show no difference, in response within each group, within each of these subgroups. We tried to make these subgroups very homogeneous, the same, at least along this confounding factor. We know the treatment, which is the lighter, did not cause the response. And because we see different rates of cancer dependent on how much people smoke, the confounder, smoking, causes cancer. Okay, so that's the idea. Now, it's not usually, sorry I made that so, why is that happening? I think it needs like something there to focus, or there. Okay, so it's not going to ever be this simple, right? I mean, it could be this simple, but this is a classic with everything that you learn. I think if you look at the simplest case without complications, that you can then, like, you know, this best experiment, the ideal experiment, the simplest case of confounding, you have in your mind the logic of it. And then it's much easier to deal with more complicated cases. So what would have happened if they don't necessarily have to end up balanced. We could have still seen an effect, maybe a lesser effect, right? There could still be other confounders. We could have seen a reversal. It could have been, there's a lot of different things you can see, but this is the simplest idea. All right, so now I just want to remind you that there is 2 ways to control for these confounders. I'm going to write it here. I should have written it in the notes, but I just want to remind you that this is the visual behind what we're going to be doing when we do modeling. So there's 2 ways to control. So many uses of the word control. Eliminate the effect of confounders. In observational studies. We don't need to do it in randomized experiments. In non-randomized, you do. The first way is stratification, and that's what we have above. And the second way is modeling. And what we're going to do is, with modeling, is we're going to include the confounder as an independent variable, as a predictor of the response, as a predictor variable. Covariate, often they say, as a predicted variable in a regression model. Oops, in a regression model. It's because my hand keeps touching something here. I'm not sure what I did, though. I'm very sorry. Here. Touched one of these things, but I don't know which one. Okay. Should I turn on and off? That might work. So we want to include this we'll be doing a lot where we just think something's a confounder, and then we'll include it in our regression model as one of the predictor variables. But I'm just trying to figure out what's going on here with this thing. So you at home just take a little break. Oh, we're back. Good. All right. Okay, so including the confounder as a regression. It's taking a while thinking. In a regression model. All right, what are we going to do next? We've covered a lot, but we have a lot to do. And that's going to be in chapter 28. So now let's see if I can, now that you've got the basics, maybe I can speed it up a little bit. I apologize if I'm going too slow, but people get so confused on this. It's confusing. Confounders are meant to be confusing. Okay. So now here's these examples. I think you can do this one on your own. These are examples of observational studies, and you're supposed to try to find what are the likely confounders and how would you adjust for them. So smoking and liver cancer, I think you could try this one on your own because, observational studies show that smokers do have a higher rate of liver cancer. So what could be the possible confounders? List differences between people who smoke and don't. This is a good one, and I can post or show you the filled-in notes next time. And sunscreen and cancer, maybe we should, and the last one we already did. Okay, so let's do this example of sunscreen. Let's try that one. Okay, so we'll skip for now. Try it at home. And now let's look at this one. Observational studies have shown that people who use sunscreen have a higher rate of skin cancer. So you see this association, sunscreen, cancer. Okay, so does sunscreen you see this association between sunscreen and skin cancer. So do you think it causes it? It might. We don't know. This is an observational study. Or there's another possibility that you see this association because there's a third factor that we haven't identified yet that's causing both the skin cancer and people to use the sunscreen. So you think, this one would be some ingredient, and actually there was one. So this would be a carcinogenic ingredient, and there was one that they identified that they eliminated. So there was some of this. I think it was called PABA, for example. PABA. You always see PABA-free sunscreen. They think that might cause cancer. Or there's a difference between people. Think of the differences between who uses sunscreen and who doesn't. That could also cause cancer. Can anybody think of a difference? Go ahead.
People who use sunscreen more often are more likely to spend more time in the sun.
Exactly. Sun exposure. Let's see if it fits in here. If you spend time in the sun, like I did, and I actually have gotten some, warning to y'all, gotten some precancerous stuff on my skin. I used to live in California. I spent a lot of time in the sun. So sun exposure causes cancer for sure. Skin cancer. Do not spend a lot of time in the sun. Okay, sun exposure causes cancer. That's a difference between people who use sunscreen and people who don't. Maybe we should do this. We're looking at differences because if there's no difference, in a randomized study, this wouldn't happen. So we're looking at differences between the treatment and the control. And the treatment is sunscreen and the control is no sunscreen. It's best to write this down to not get confused. Okay, and he said sun exposure. People who, aren't going outside aren't going to, more sun exposure, less sun exposure. Okay, so that's the idea. So then, and it's also a cause of cancer. So this is a confounder for sure. You have to compare people who spend equal amounts of time in the sun. And when they did that, sunscreen prevents cancer. It doesn't cause it. So this is very important because if you think you're in this situation, and I've seen many articles, don't use slather sunscreen, you're going to, cause cancer, you'll stop using sunscreen. You stop using it if you're in this, and that would work if you're in this situation. If you stop using sunscreen, you don't have the cancerous carcinogenic ingredients, you don't get the cancer. But if you're in this situation, you stop using the sunscreen, you're still going to get cancer, and it might be worse, and it is. Sunscreen is actually preventing cancer. So if we did our stratification, the scales would be tipped the other way. It would go in the other direction. What looked like caused cancer actually prevents cancer once we go into once we stratify. All right, and this is the one we just did. So we'll say see page 5. We already did that one. All right, so now what's our next thing we're going to do? I'm just going to briefly talk about this page, that sometimes observational studies will have cause and effect reversed. Let's skip these two, and let's do this last one. You'll get the idea. And you don't have to fill these in unless you want to. I think you'll get the idea. It's a simple idea. A study showed that people who drank lots of diet soda are more likely to be obese than people who don't. There's been a lot of studies like this, who don't drink diet soda, and concluded that the artificial sweeteners may set up a craving for sugar that leads to weight gain. It wasn't, these subjects were looked at the same time. It wasn't a study where they tracked people, none of whom started off heavy, and then the ones who drank the diet soda got heavy. It wasn't like that. They just look at a slice in time, cross-sectional study, and they said, hey, people, they see this association, diet soda and obesity. And they think, oh, the arrow must go this way. And then they look for the causal link. They look for what's doing it, and they came up with this idea that somehow these artificial sweeteners, this is their causal link. This is directly quoted from one of the papers. Okay, so that's what they think. But isn't it just as likely that the arrow goes the other way? I mean, I think that heavy people often go on diets, and part of that is diet soda. They want to lose weight. So I think it's more likely, or just as likely, seems more straightforward to me, doesn't it to you? I mean, time, 30-second story, true story. I had a girlfriend who was quite a bit overweight, and she knew I exercised a lot, so she said, take me to your gym. And I said, sure. But I took her, there were different classrooms going on, and I took her to one where the workout was much easier, and there were a lot of heavy people there. And she says, no, I want to go to the one you go to, because there's heavy people. They're like, I don't want to, the workout's making them fat, she said. Those were her words. That workout makes them fat. I said, and she thought if she went to a much more intense, the other workout would make her skinny because there were skinnier people there. But it wasn't, it was crazy to think that. It's the cart before the horse, right? I mean, it was designed to help heavy people lose weight. All right. So association, just be careful of the direction. All right, you're bearing with me. It's a lot to cover, I know. This is a paradox. It's quite interesting, called Simpson's paradox. It's a very well-known paradox, and we basically just hinted at it with the sunscreen example. It's an observational study where there's such extreme confounding that once you break into subgroups, the direction is reversed of something that you think is good for you. Once you break into has a positive result. Once you break into subgroups, has a negative result. So here's a classic study that was done a while ago in England on smoking. And it looks like there was a 20-year study that followed people from 1974 to 1994, 1,314 British women, and compared the death rates, right here, here's what they looked at. They compared the death rate of smokers to non-smokers. And they see, whoa, this is crazy. Non-smokers die more. So they thought, hey, does smoking prolong your life? This got my attention because I used to be a smoker. I said, maybe I'll take it up again. I'll live longer. But let's think, it's an observational study, and a little background is that, let's just look at this. You notice something. In the smoker group, there aren't very many old people. Now, why? Not because they've died off already. No, the study started in 1974, over 65. Okay, so they're over 65 in and then 20 years later, they were old. So they all had a high death rate. Whether they smoked or not, it looks about the same. This one looks a little bit, I mean, you get old, you die, whether you smoke or not, right? But the thing is that these people, there are many more non-smokers. Just because back in the day then, when people started smoking, for women it was looked at as masculine. You weren't allowed to wear pants, you weren't supposed to smoke, you weren't supposed to do anything that was non-feminine. I wasn't even allowed to wear pants to school. No joke. All through high school. So there was a lot of taboos. And even though I'm not this old, it was similar. So people who smoked, there weren't very many. Now, so that's the problem is that the confounder is age. So you see that not smoking, right here, I'm trying to do this, not smoking, you see that that is connected with death. More death. You die more. You don't smoke, not smoking is connected with more, you die more. More death. Okay? But why? The non-smokers are old. So age is the confounder. Age, if you're old, you die more. And for some reason in this, because of this particular historical circumstances, old people were not smoking. So the idea is that these overall results, before you break into subgroups, show that the overall results are misleading. Showing what? Showing that non-smokers die more. But once we break it up into these subgroups, we have 3 subgroups, and do these comparisons. So here you go. Look, overall, right? This group, 31.4 versus 23.9, overall. And isn't it a paradox? You'd think they take the whole population, you break it into groups, and in no group, not a single one of them, is this, are the non-smokers. Do you see that same relation? The non-smokers are bigger here, but look, here it's the smokers are slightly bigger, here quite a bit bigger with middle age, and here slightly bigger. So isn't that paradoxical that you can have an overall result that is one direction, and you break the entire population up into subgroups, and within every single subgroup, it's the opposite direction. You must think, how can that happen? Right? And the idea is because the non-smokers had a high overall death rate because 193 out of the 732, the big proportion of them were old, and also, well, only 49 out of the 582 of the smokers were old. So old people die more. That's all it was. Okay, so within each subgroup, smokers die more. It was dramatic in the middle age group because look, smoking takes a while to kill you. So 20 years later, the oldest people were only 54. You're not usually dead yet. So that's why it had a low. Smoking, the death rate isn't going to show up till later. Here, if you make it to be, when you're that old, you're going to die whether you smoke or not. So it's in this middle range. They started off 35 to 64, and 20 years later, some of them were in their 80s. They were 55 to 84, and there is where you see the most difference. So it's just important to look at data and see what's going on. So it's Simpson's paradox says that the overall percentage is misleading because of confounder. Once the confounder is controlled, this is what it is. The overall effect is reversed. So you'll see it referred to a lot as extreme confounding. And that's what it is. And it only happens in observational studies. So let's just highlight that. Now, I think we might be able to finish. Let's see what else is. Yeah, we'll finish the main ideas. So we have 5 minutes left, don't we? Or not? Do we have 5 minutes left? I think we do. Yeah. Okay. Are you able to do it? I mean, I know this is getting like a long stretch. But I think I'll yeah. This class ends at what? 1:50, right? Okay. So let's just do this. And, all right. So this you'll run into a lot. In long-term studies, people drop out. So even if a study starts off extremely well, as a perfect study, what do you do? What do you do with people who drop out of randomized experiments? So a study can start off perfectly randomized, but become observational within it because people self-select to drop out or not. So this is a big issue in medicine where you do long-term studies, and let's think about how we would analyze this. All right, so here's a medical trial. It was randomized. It was a perfect randomized controlled double-blind experiment, and it lasted 5 years to see whether middle-aged men with heart disease, to see if that drug would prevent them from having heart attacks, because it lowered, everybody thought it would, because it lowers cholesterol. So the death rates between the two groups were basically the same. Where am I looking? This overall death rate. Now, you were just told on the previous page, don't trust this overall, right? But let's remember, that was because they were unbalanced. That was an observational study. You have to make them more alike. This one started off completely balanced. This was randomized, so they were randomly assigned. It was an ideal experiment. So look, so where is this? What happened? So let's look at the numbers. Overall, there's no effect. But then, and this really happened, people argued, wait a minute, this drug can't help you if you don't take it. Adherers were people who stuck with the program and took the drug on a daily basis. Non-adherers took it either sporadically or quit or dropped out, okay? So if you look at people who just took the drug, there were only 15% died versus the non-adherers who didn't take the drug. Well, the drug can't work if you don't take it, they said, so it proves the drug worked. Now, this was the placebo, and they didn't really look at it very much, and so they said, this is the comparison we should make. Which comparison should be used? This one, the 25% that shows the 15% death versus 25, that shows the drug worked. Everyone to everyone, or maybe you want to do adherers, something else. Like maybe, if you look here, you see that those who stuck with the program and took the drug, they were assigned to they didn't know which group they were in, they have the same. And same here. So it looked like the drug didn't work well, what do you want to, we don't have much time to discuss it, but anybody have an opinion? Does anybody think we could do this comparison? I don't think we should, because if you have a placebo, you see right away that those who religiously took it, the 15 versus, so they agree. So in this case, it looks like you certainly don't want to do this. This, you know. You don't want to do that, because that clearly is wrong. Now, in this case, it doesn't matter. And let me just tell you, the best practice is to use everyone, and I'll explain why in a minute, everyone in treatment to everyone in control. So this is the one you want. Otherwise, because these groups are self-selected, and it breaks the randomization. How is that a problem? So it introduces bias. It's a problem when you, for example, many studies don't have placebos. So people look at this, they see this, and they say, no, like this is on exercise, right? This is the random assignment. And they say, wait a sec, exercise is not going to help you if you don't do it. Look, the people who exercise, these are the same numbers, we just don't have this. Because in non-drug studies, in many studies, you can't. So here, people will often do this, and you can see why it's wrong. Because you don't know, the people who adhere are systematically different. They might be responsible in other ways. They tend to be people who are regular in their habits and follow directions and listen and so forth. So they tend to be systematically different and often do better in trials than people who drop out. Okay? So there you know that you want to do this to this, and it's pretty obvious. But the problem is that sometimes the treatment itself is going to make people adhere or not, and you want to know that. So here's another example, and we are about to go. But the question is that everybody has, and naturally I've seen it, doctors and everybody ask me, why not compare adherers in treatment to adherers in control? Why not? So remember why we do these things. We need to make sure the groups we compare are nearly identical before the treatment starts. And the adherers select themselves. So there could be systematic differences, especially due to drug side effects and so forth. And we want to know that. People will drop out for different reasons. So I always like teaching examples, and I thought this might help you. I did this one semester, or I thought of doing this, but I imagined this could be the scenario and didn't do it. Okay, I wanted to do these challenge instead of the standard bonus. So pretend I randomly assigned people to do, I just wanted to see whether people would do better if I did harder problems or easier problems for our bonus pre-lectures. So I was going to do this experiment, and this was the big danger that I worried about. So you randomize the people into the challenge and the standard, it's just for bonus, and then everybody gets randomized. Let's say there were 1,000 in each group. And the overall results show that the standard bonus was better. But I thought, let's look at who stuck with it and who would continue if things were really challenging and they were bonus. Probably this would just the students who were smarter to begin with so it wouldn't be helping everyone. It would just, so I couldn't, when I compared this, subgroups, then I see something really different. So I don't want to compare the 96 to the 90 here, the 80. It's very confusing here. So I think it's best to compare everyone, because those who stick with it, look how many people dropped out here compared to those. So this is hypothetical results, and I'm not sure it would happen this way. But the idea is the comparison you want to use, because the treatment could actually cause people to drop out or have side effects, or you know what I mean, so that you don't want to disrupt that. You want to know that. You don't want to just ignore that. So the bottom line is never compare. This is, we'll talk about this more, and it's very important. And the bottom line is to never compare groups where the treatment might affect what group they end up in, like if they self-select. You can look at males versus females separately for sure, because they were in those subgroups before the treatment was administered. And you'll see that all the time in medical studies. But you don't want to look at anything where the treatment might have been the cause of why they dropped out or not. So if you look at subgroups, they have to be defined before treatment. And keeping the original randomization by combining all those, this is what you need to do in randomized study. If it starts off randomized, don't screw it up. But combining all those originally assigned, whether they're here or not. It's called intent to treat analysis, and it's the gold standard in medical studies. It took a while to get there. It wasn't initially. So, and it's like Simpson's paradox, except for randomized experiments. So basically, if it's random, we'll summarize it next time, but you've had enough today, and we'll go over the summary and do this next week. But you have all the materials that you need to do homework 1 and 2 that's due next week, next Tuesday and Thursday. And check out the pre-lectures, and have a great weekend.